scroll down. Last page is always important. Here we have everything listed. October 18th, today, frame and grid equations we are going to discuss. This is chapter 5 of our textbook. Last week we had our midterm exam. It was because of the problem that it didn't transfer the pictures, but we will have it next week on Monday. The same procedure, the same thing you did. There were 10 questions, you answered 3 of them, so 7 remaining. Those 7 we will have it Monday next week. So again, you go on time to Canvas, go at 10 o'clock. It starts at 10, and I have not made it yet, but there would be 7 questions. So last time it was 45 minutes. So we will have the same 45 minutes, possibly if a little bit different. Canvas writes the time which is left and the time for the test, but most likely around 45 minutes, 7 questions that you are going to answer, whether it is multiple choice or whether you enter your answer, and for 45 minutes or so, and then we will have our class afterwards. So 10 o'clock you start, and then we have our class, even if it is for a shorter period of time, that's fine. But we will have our class afterwards. So if there is a break, 10 minutes or so, then we will have our class, let's say at 11 o'clock. So 10 to 10:45, possibly you complete the test, and then possibly at 11 o'clock, we will have our class. Even for, we have half an hour or 40 minutes or so, that would be fine. So 11 o'clock, we will have our class. The test, the same format as what it was, 7 questions remaining, and then you calculate something, you enter your answer on Canvas. Canvas, remember, it doesn't accept late work. It doesn't, if the internet doesn't work, then you have to make sure that internet works and your Canvas works and everything works. Otherwise, you can take the test on campus, actually use the computers on campus. It is more, you are assured that it would work. All right, so that is, the question is whether I will be available on Zoom during the test. No, there is no need that I be available on Zoom. You can directly go to Canvas and take the test. It says, previously I called it midterm, so I call it midterm. The same, you will see midterm possibly continued or midterm, let's say 2 or midterm continued, either one. But you will see it under modules or under assignments or under quizzes, everything it shows. All right, that would be our plan for the quiz next week. The same format, the same as what we did, no new material. All the material that was covered in the previous one, the same, no new material added to that. That would be about the test. The week before, we talked about beams. And so we covered trusses previously, we talked about beams, we had our midterm last week. So today it is chapter 5, talk about frames and grids. And then next week, from next week after our completing this midterm exam, we will have our plane stress, plane strain problems. We are going to move on to chapter 6 and talk about plane stress, plane strain problems. So with this, let me go to modules. For this week, we have This is frames. That is what we are going to discuss today. Examples are in buildings, bridges. What are they? Well, these are beams which are rigidly connected to each other. They are either welded or they are bolted. If it is bolted, of course, we can dismantle. Disassembly is possible, but if it is welded, then we cannot dismantle this. It would be destructive dismantling, of course, of this. So this is a discussion sometimes in civil engineering department, whether they want structures to be welded here or bolted with a gusset plate we add and then bolt them together. More heavy duty loadings, you can apply the load anywhere. Unlike, for example, trusses that we are just limited to apply the load at the joints, at the pins. But here we can apply the load anywhere, moment or any type of loading and anywhere on the structure. If this load is in the plane of this frame, then it is called frame simply. But if this load is perpendicular to this plane that you see, to the plane of this structure, then it is called a grid. So by frame, we usually mean that these loads are in the plane, but if it is perpendicular, it is called a grid. Today, we are going to look at finite element formulations for frame problems and look at an example problem. In the lab, we already used these frames. So today, we are going to look at the formulations of what it was. Has a lot of similarities actually with the method that we did for the derivation of trusses, the same pattern. This is one of these members. It is oriented at an angle theta. We always measure theta counterclockwise positive. So this is positive. Two coordinate systems are defined. One here, xy, this is the global coordinate system, and x prime, y prime. This is the local coordinate system. This coordinate system is attached to the element, goes from this node to this node. Now, at each node, we have 3 degrees of freedom. We are applying a force in the x prime direction, call it F1 x prime. A displacement associated with this force is U1 prime. There is a force also in the y prime direction. It is called F1 y prime. And a displacement V1 prime. And a moment, M1 prime, and angle of rotation, Phi1 prime. This is at this node and the same at the other node. F2x prime, U2 prime, F2y prime, V2 prime displacement, and moment M2 prime and rotation V2 prime. Now, anybody can tell me how many degrees of freedom per node do we have here? How many degrees of freedom per node? Anyone?
Two.
What are they? What are these degrees of freedom? We have a displacement in the x prime direction. This is U1 prime. We have a displacement in the y prime direction, which is V1 prime. And we have also a rotation because of this moment. The job of this moment is to rotate. And there is a rotation, V1 prime. So how many degrees of freedoms do you see here?
3.
There are three degrees of freedom per node. And then this element, how many nodes that this element has?
2.
2. So our element stiffness matrix would be what size? You said 3 degrees of freedom per node, and there are 2 nodes. So our element stiffness matrix would be
6 degrees of freedom.
6 by 6, 6 degrees of freedom. So it would be a 6 by 6 matrix.
This is for all beams in this section.
This is for, of course, we are talking about frames, but in general, yes, actually beams also, but in the finite element formulations, we consider 2 degrees of freedom. Displacement, for the formulation, we did displacement in the y direction and also rotation. If you look back to the derivations for beam problems, we consider displacement in the y direction and rotation, because this axial we had already done. So in our formulations, we didn't do, we didn't consider this degree of freedom, but we added this later. After we did our formulations for beams, then we added this one because of this was for a bar subjected to axial loading. So we added this degree of freedom later. But in our formulations for beams, we consider 2 degrees of freedom, displacement in the y direction and rotation. But we added this one later. So yes, there are 3 degrees of freedom per node for frame problems. Now, our goal is always, objective is always to find the element stiffness matrix. Element stiffness matrix, but in global coordinate system. We don't want it in local coordinate system. We don't want it in x prime, y prime coordinate system. We want it in xy, in global coordinate system. So again, as usual, as what we did for trusses, we find k prime. Everything with prime, it refers to local. Everything without prime, it refers to global coordinate system. So, well, in order to do this, let me see, I have this one. Our formula, as we can write this is actually a beam element. So we can just write it F prime is K prime D prime in terms of its local coordinate system, the same as what we did for beams. But everything here is with prime. We don't want this prime. We want to get rid of this and write it in global coordinate system. It means without these primes. Our job is to find this K prime, drop this prime and make it K. So we want this K actually. So in order to do this, well, let's first use this formula that we have in local coordinate system. This is F prime is equal to K prime times D prime. F prime is forces in the force vector in local coordinate system. It is F1 X prime, F1 Y prime, M1 prime, and the same for node 2. This is our element stiffness matrix in local coordinate system. Remember, for beams, we already did this before. It was, remember, EI over L cube. But here we are just simply adding F1 X prime. So we are just adding this one. This is for node. This would be U1 prime, V1 prime, V1 prime, U2 prime. So as you see here, we are doing C1 minus C1 minus C1, C1. So, and then we have our C2, which refers to that beam EI over L cube that we derived before. But C1 is AE over L. So these are the substitutions that we are using just to make it simpler. C1 is AE over L and EI over L cube for C2. This is K prime, but in local coordinate system. And this is the displacement vector, U1 prime, V1 prime, V1 prime, and the same for node 2. We want to get rid of this prime here. How do we do this? Well, we did it for truss problems. Remember, in trusses, we said that D prime is TD and F prime is TF. This one, D prime, is related to D, which is in global coordinate system, by a transformation matrix. T, we called it transformation matrix. So this we can transform local to global. The same for forces. Displacements and forces are vectors, so they transform the same. So here, our T matrix is given by this. Cosine, sine, negative sine, cosine, as what we did before. This is for the actually rotation that we are adding. So this would be the transformation matrix for these elements. Using this one, make this substitution here. You see, for F prime, use TF. For D prime, use TD. So we are getting rid of these primes. So let's do this. F prime is K prime D prime. For F prime, use TF. For D prime, use TD. That's what we get. Now, multiply both sides by T inverse. So this is T inverse TF, and this is T inverse K prime TD. This T inverse times T is what? Anyone? What is T inverse times T?
Identity matrix.
It's identity matrix. Very good. Yes, it's identity matrix. So we can just remove this one. So we have F is equal to T inverse K prime T D. But this T inverse, we don't like this inverse here, because inverse of a matrix is always a lot of some problems, because very time consuming. Finding the determinant of, let's say, even we easily have 100,000 by 100,000 matrix. So inverse of this is, if even the determinant is zero, then it causes ill conditioning and singularity. So very time consuming also. But the good thing is that inverse of T is the same as its transpose. Remember, in the actually first activity, we did it for a simpler version of T. That was a 2 by 2 matrix, but it's the same thing actually. So this is orthogonal. This property is called orthogonality property. So we drop this inverse and write it as T transpose K prime T, and this is D. That is our formula. F is equal to something multiplied by D. This something, it is called element stiffness matrix in global coordinate system. That's what we wanted. It is T transpose times K prime times T. That is what it is here. Now, what is this T times K prime T? We have everything here. This is T, so transpose of this one, times K prime. This is K prime. We start, this is K prime here, this. Times another T, here we find element stiffness matrix to be given by this. We said this is a 6 by 6 matrix, and it is a 6 by 6 matrix. This is 1, 2, 3, 4, 5, and 6. And this is symmetric, so we are not rewriting this piece here, but we use this symmetry. Very important in finite element formulations and solutions. Symmetry always plays an important role in reducing the number of these computations and memory usage. So this is what we wanted. E, modulus of elasticity, length of the element, area, cosine of the angle that this member makes with the global coordinate system, I, area moment of inertia, sine of the angle, and everything else, area, cosine, I, sine, and everything else we can find. And use this one. Once we have this in global coordinate system, we put them in together by direct stiffness method to create the global stiffness matrix and then solve for displacements. All right, that's all I wanted to discuss. The rest is now solving, looking at an example problem. Any questions before looking at this example? No questions. So let's look at this example problem here. Node 1, 2, 3, 4. This is a frame like this. 10,000 pound force here, moment applied here. 4 nodes and 3 elements. Element 1, element 2, element 3. X, Y, this is our global coordinate system. This is subjected to these loadings. The question is, we are given XY global coordinate system, E modulus of elasticity is given, area, I for elements 1 and 3. So this element 1 and 3, I is 200. For element 2, this is 100 into the power 4. So this area moment of inertia. So this is the frame. The question is to find the nodal displacements and rotations, and also we want to find forces and moments in each element. To solve this problem, first item is to create the connectivity table. You have your paper and pencil ready. I want you to be also active, use your time here. I want this connectivity table. Write this down. Connectivity table, 1 minute. Create the connectivity table and let me see what you do. All right, let me also, I have this camera here. This is the node 1, 2, 3, 4 here, and we have connectivity table. Node, we have here element, node I to node J and angle theta. Tell me node element 1. So we call this element 1, element 2, element 3. Element 1 goes from what? Node, what is it? Element 1?
1 to 2.
1 to 2. Angle theta?
90 degrees.
90 degrees. All right, very good. Agree with your friend, 90 degrees?
Yes.
Yeah.
All right, very good. Element 2 goes from what? Node
2 to 3,
2 to 3, angle theta.
0 degrees,
Very good. And element 3 goes from
3 to 4,
3 to 4, theta.
90,
270.
270, you use, somebody said 270 or 90, let me see.
Oh,
I-
would 90 be from 4 to 3?
Yeah, it would be minus 90 or 270.
Very good, you're right. Pay attention that, yes, you were right. When you say element 3 goes from node 3 to 4, so if it is 3 to 4, this would be our x prime axis, and this is our global. So this angle, it is clockwise, it is negative 90, or you can also use positive. We said counterclockwise is positive, so we can use 270 degrees. So both of these two are correct.
Is there any problem with writing it from 4 to 3 and positive 90?
Absolutely, it is correct. You
Okay.
can write node 4 to 3 and use positive 90 degrees. The only problem is a little bit when we create the global stiffness matrix, we have to pay attention to the degrees of freedom and put them in the right places. You see, then if it is 4 to 3, then our, you see what you create. So it would be from node 4, if you say 4 to 3, so we are disordering this. So when we create the global, we have to switch them. So we have to pay attention to this.
Okay, I see.
But otherwise, it is correct. There is no problem with this. It's just computers don't mind. Of course, computers do it all the time. So computers, whichever they do it 4 to 3 or so. But because for computers, they have addresses. So this address just directly goes and puts them. But for us, we have to pay attention to this. All right. So this is the this is the connectivity table. Next step is to find the element stiffness matrix. Next step would be I need to find now K for element 1. We said that it is E over L, and this would be, we said that it is for this 6 by 6 matrix. 3 degree of freedom per node and 2 nodes, so 6 by 6. We need to find it also for element 2, whatever it is, and again we do it for element 3. Now, after creating this, we need the global one. What is the size of this global stiffness matrix?
9 by 9.
9 by 9. Agree with your friend or not? Anyone? Agree with your friend or not?
Yeah, I think so.
That is not correct.
The 12 by 12?
12 by 12. Agree with your friend or not? 12 by 12. How many degree of freedom per node do we have?
3.
3 degree of freedom per node. How many nodes do we have in this structure?
4.
That makes it 12. This is node, so that is 12 degree of freedom. That would be the global stiffness matrix. It should be 12 by 12. So it is not 9. It is 12 by 12. And then we have to apply the boundary conditions. I'm reviewing these items so I can show you with the going to the canvas. It is 12 by 12, but I have to apply the boundary conditions also. What boundary conditions, how many equations should I remove? Then we end up with how many equations, how many unknowns.
Nodes 1 and 4 are fixed so that they can't translate.
Okay. And also they can't rotate. So how many equations do I remove? We said that it is a 12 by 12. So I want to see when I apply the boundary conditions, when you do it in FEMAP, what is happening? How many
Remove
equations?
6 equations.
6 removing, very good, you're right. So 3 equations from here, displacement in the X, Y, and rotation out. The same for this one. So 3 and 3, 6 equations and 6 unknowns out. So we end up with 6 equations and 6 unknowns, but we need to solve. All right, let me go back to Canvas, and now we know where we are going. So that was the connectivity table. This is this one. We talked about this. I used 270 degrees or negative 90, the same thing. We need to, for each element, element 1, this would be K1. All of these parameters, angle theta for element 1, we said it is 90 degrees. So cosine of 90, it is 1. And cosine of 90 is 0, sine of 90 is 1. And we have everything else. We can create K1, degrees of freedom, write them down here so we know the addresses. U1, V1, Phi1, U2, V2, Phi2. This is the global element stiffness matrix for element 1 in global coordinate system, of course. This is this one. Do the same thing for other elements. For element 2, we said theta is 0 degrees, cosine 0 is 1, sine 0 is 0, and then other parameters, this is K2, degrees of freedom from node 2 to node 3. Element 3, theta is negative 90 degrees or 270 degrees, cosine is 0, sine is negative 1. This is stiffness matrix for element 3 in global coordinate system, degree of freedom from nodes 3 to 4. And then the global stiffness matrix would be, as what we discussed, 12 by 12, but it's a very large matrix to write it. We can apply also boundary conditions, U1, V1, Phi1, 0, and U4, V4, Phi4. These are the 2 fixed nodes, and applying them, we get this one. Now, I need to write the force vector. For this problem, I need to write the force vector now at node 2. This force is positive or negative, I should write in the force vector.
Positive.
Positive, you're right. This is to the right, according to our sign convention, it is positive. This moment, I should write positive or negative.
I believe positive, because it's counterclockwise.
You're right. It is counterclockwise positive. You see, according to our sign convention, always for beams, frames, the same. We said counterclockwise positive. So yes, this is a moment which is counterclockwise and it is positive. Therefore, plugging everything in this is 10,000 pound force that we are applying, everything else 0, and there is a moment of 5,000 pound inch. This is the system that NASA needs to solve for these displacement vectors. 6 of them, U2, V2, Phi2, U3, V3, Phi3, solving, that is what we get. U2, V2, Phi2, U3, V3, Phi3. These are the displacement and rotations at this node. That's part A of the problem, finding displacement and rotations. Next step is to find the forces and moments in each element. Once we have this, everything else is now post-processing, not a big deal. But remember, again, like what we did for trusses, we need to find the displacements in local coordinate system to be able to find the forces and moments in each element. Because forces and moments in each element are written in terms of local coordinate system. But these displacements are in global coordinate system. So we have to find them in local coordinate system. We can do this easily. TD, remember we said D prime. Let me go back and show you. Remember, this is D prime is TD. We found the displacement in global. This is the transformation matrix. Multiply, we get this displacement in local coordinate system. So here it is. This is transformation matrix for element 1. This is for element 1 here. Zeta is 90 degrees, so cosine 90 it is 0. So this is 0 and sine it is 1. So this is the transformation matrix, and displacement, it goes from node 1, it is fixed, everything is 0, and node 2 that we have this for node 2, we have the displacements here. So these 3 items go here. These are the displacement in local coordinate system, and then now multiplying it by K prime TD, this is TD, K prime element stiffness matrix in local coordinate system. It is this one, multiplied by these displacements in local coordinate system. Here we find forces in element 1 to be like this. This is F1 X prime, F1 Y prime, M1 prime, F2 X prime, F2 Y prime, and M2 prime. Everything you see in terms of primes, these are in local coordinate system. Do the same thing for elements 2 and 3, not a big deal. The same procedure. We have the displacement for element 2 and element 3. Similarly, we get these forces and moments in elements 2 and 3. Now, a very important question. Any questions you have? Because I have a question for you. Any questions you have? All right, no questions. What I want from you to do, very important practice here, you have your paper and pencil. These are the forces in element 1. I want you to draw element 1 and show these forces acting on element 1. In practice, in industry, we do these things, and then we need to show them on the free body diagram, and then we send it to other departments. Let's say here we send it to civil engineering department so they can design the foundation, because this node 1 it is attached to the foundation here, so it is attached to a support. So here they need to use this one to design the foundation, the pedestal, and the reinforced concrete here to handle this load. I need you to, what I would like you to do, this is element 1. This is element 1. Draw this element 1. All right, this is from node 1 to 2. You did it. Node 1 to 2, draw this, just this element, just element 1.
Do we include the 10,000 pound force acting at node 2?
No, no, this is not, this is at the node here. This is just the element itself is not this one. This is at the node. This element is attached to the node. This load is at the node. So
Okay.
here, just draw this free body diagram of this element. Node 1 to 2. And show these forces that we found acting on this element. These are the forces acting on this element. Show them on this, because then we have to make sure that equilibrium is satisfied. Important practice, 2 minutes, show all these forces. Let me see what you have done. All right, I have to show the camera. Now, this is for this node 1, node 2. Well, I cannot show the numbers, and also I can show one at a time, either the camera or canvas. So let me, you have the numbers. Let me see, what did we have for F1x prime? We get negative 3,700. You see, this is node 1, node 2. This is our x prime axis. Do you see it? Now, our x prime axis is going upward, and this is our y prime. Remember, this is in local coordinate system. So this is 1, 2. This is element 1. F1x prime, we found 3,700 pounds. This is our x prime axis. So upward is positive. So this is 3,700 pounds. It is the force. F1y prime is positive to the left here. We got 4,990. So there is a force, 4,990 pounds. And there is a moment of 376,000 pounds each. What do I do? Should clockwise or counterclockwise? Which one should I do?
Counterclockwise.
Counterclockwise, very good, because our sign convention is counterclockwise positive. So this is 376,000 pound inch. Do the same thing for node 2. For node 2, f2 x prime, it is 3,700. It is positive, so this is 3,700 pounds. F2y prime, it is negative 4,990. 4,990 is negative in the y prime, so negative, it is positive to the left, so this is negative to the right, which is 4,990. And finally, there is a moment, 223,000, and it is positive, so counterclockwise, it is 223,000 pound inch. All right, this is the free body diagram of this element 1, and it is very important that we do it correctly. Everything that we have done, this is the result of this analysis. If this is wrong, then it's worthless. We didn't do this properly and no value. Must check whether equilibrium is satisfied or not. 2 minutes, tell me, is equilibrium satisfied here or not? This length was 10 feet. Equilibrium is satisfied or not? Anyone?
Equilibrium is satisfied in the X and Y forces, but not the moment.
Not the moment. Anyone agrees with your friend that these two are satisfied, but not the moment? Anyone, any other opinions?
I also got that result.
Yeah, it's off by 200 pound inches.
By 200 pound inch. Now let's check F prime in X prime. So this is 3,700 and 3,700 downward, upward. So that they cancel these two forces, 4,990. These two, they are the same. So this is counterclockwise, and then this force times. This is 10 feet. Pay attention, the units. And so these two are satisfied. This one, 200 pound inch. What is your, what do you think about this? What is your justification? Yes.
Likely rounding.
You're right. In rounding these numbers, I mean, they were not really 2,200, 223,000, or, I mean, these are rounded. The author rounded, and then that's what this roundup errors made this 200 pound inch. But if we carry these decimals or so, it is not. So it is satisfactory and equilibrium is satisfied. So, but this practice is very important, that you be able to show these forces acting on these structures, because you see it is connected to a wall, connected to a foundation after all here. So this is what civil engineers need to know, these forces, so they know what forces this foundation is carrying. So if this is, let's say, then usually they design the, for example, the structure. This is reinforced concrete. This is the ground, let's say. This is the ground. So this comes out and they apply this base plate here and then put the structure on top here. So this is node 1 that you see here. So all these forces that you see here are applied to this underground. This is underground. So civil engineers need to design this and these dimensions and this height, and make sure that everything, these forces that you found here, you tell them based on this, they designed this foundation here. All right. Let me go back to our canvas. Any questions about these forces and moments that we found in element 1? Do the same thing for elements 2 and 3. The same procedure, we find forces and moments in elements 2 and 3, and then also check equilibrium is satisfied here in element 1, like what we did. And these are also shown here. So these are the forces and moments actually in element 1. This is for element 2, and this is for element 3. So we have all of them all also here. I think in addition to all of these, I added one more item here, equilibrium of node 3. What we looked at, they were, we showed the equilibrium of each element, but for the node 3, see if you go back, node 3 is here. Node 3 is connecting element 2 and 3. So this node 3, some part of this comes from this element 2, some part of this loading comes from element 3. So when we want to draw the free body diagram of the node itself, there is a moment, concentrated moment. This at the node, we need to show this 5,000 pound each. And the forces and moments in each of these two elements. But pay attention, the forces that we showed were the forces that the node applies to the element. So the element applies forces and moments in the opposite direction to the nodes. So here, going back to this, first of all, this was a concentrated 5,000 pound inch moment. Now, from element 2, I have shown it for element 2, it is in red. For element 3, it is in blue. For element 2, these are the forces and moments. Look at for element 2, for example, this is element 2. This force of this axial force is 5,010 pounds. It is to the left. This is the node that is applying this force to this element. This element applies the force, the same force, but in the opposite direction to the node. So 5,010 would be to the right now. This 5,010 to the right. This is what this element is applying to this node. And the same, for example, here, there is a force 3,700 pound that the node is applying upward to this. So this element applies in the opposite direction, 3,700 downward to this one, to this node. And the same for moment. Let me also show you. This one moment is clockwise, 221,000. So it would be in the opposite direction, 221,000, but counterclockwise. This element applies to this node. I showed it at a distance so it is clear. The same if you look at for element 3, these are also the forces and moments that element 3 applies to this node. So 1 minute, check, is equilibrium satisfied here or not? Is node 3 is in equilibrium?
Yes.
Anyone agrees with your friend?
Yeah, it is.
You are right, it is, because let's in the horizontal direction 5010, to the right it is to the left, the same amount, 3,700, 3,700, and moments here we have 221,000 and 5,000 both counterclockwise, so it would make it 226,000, and with this 226,000, yes, it is in equilibrium, and these are also the forces that act on element on node 3. So pay attention that I just wanted you to pay attention to the forces at the node and also for the elements. All right, any questions, anyone?
For element 2, if we tried to do this, would we have to include the 10,000, for example?
For
The
element
external force?
2,
I mean, node 2.
That's right. That's right. Good question. Yes, for this node 2, for node 2, you need to include this 10,000 is applied to the node. So you apply it to the node and then make sure equilibrium is satisfied. You want to do this? That would be your practice right now. Draw node 2, node 2, and show all the forces acting on this. This would be 10,000. This is node 2. This is 10,000. £10,000 it is applied here, and what we got here, these are the, use this one, this goes from element 1 and 2. Look at these items and these items, 2 minutes. Draw the free body diagram of node 2. That's what I'm also doing it here. Draw free body diagram of node 2, show all the forces acting on node 2. All right, 2 minutes. Let me show my camera. This is what I'm doing also here. 10,000 pound force. This is node 2. This is the external force. These are from element 1. From element 1, 4,990 to the left, and 3,700 downward, and clockwise moment of 223,000 from element 2. From this element here, we have a force 5,010 to the left. There is a force upward 3,700. I show it like this, 3,700. And there is a moment. This is counterclockwise. Let me show it. 223,000 pound-inch. All right. Is it in equilibrium? In the x direction, we have 4,000. In the x direction, we have 3,700 and 4,990. What do we get here? Could you check whether equilibrium is satisfied or not, anyone?
It is.
Yeah, it is.
Okay, very good. I see 3,700 and 4,990. It makes it what? It makes it
I think it's 5,010 plus 4,990.
Oh, this is 5,010, and this one makes it 10,000. Force in the y direction, it is satisfied. And how about moment? Did you check the moment here? We have 223,000 clockwise and the same counterclockwise. Yes, equilibrium is satisfied. And so all of these are the forces that these are the forces that this element 1 applies to this node, and this element 2 applies to this node, and it is satisfied. Equilibrium is satisfied. The same, these forces are applied to the node, but then the node applies the forces in the opposite direction to these elements which it is attached to. All right. That was our discussion about frames. I think, let me go back to the canvas. That was our discussion. I think I don't have anything else on frames. Any questions about what we discussed today? No questions. You see, all of these that we were discussing so far, they were line elements we used for a bar subjected to axial loading. Then we talked about trusses. Then we talked about beams. Then we talked about frames. They are all line elements. As you see here, is just one line. The element is a line. But then from next week, we are going to talk about continuum elements. They are not line elements. They are two-dimensional and three-dimensional elements. So the simplest one would be constant strength triangular elements. Next week, we are going to start with that triangular element and then continue with, of course, others, quadrilateral, and so on and so forth. The test that, again, last topic would be again, the test continuation of what we did. 7 problems, 7 questions will be on this test. It would be at 10 o'clock. You go to Canvas. There is no need to come to Zoom at 10 o'clock. You go directly to Canvas and take this. It would be under midterm exam 2, or you can find it under the module for that week, or under the quizzes or assignments. It would cover everything that it was in the previous one. So nothing new, no new material. So it was, I think the previous one, it was chapters 1 through 4. Yes, it would be 1 through 4, but not 5 that we discussed today. And it would be possibly about 45 minutes. Right after that, about 11 o'clock, at 11 we will have our class. So possibly 10:45 you finish, you have 10-15 minutes break, and then we have our class at 11 o'clock, even for half an hour or 40 minutes, we have our class, and that would be fine. We need to use our time. All right, that was about also our test. On Wednesday, we will have our activity. We did 3-dimensional finite element analysis. Part 2, you did it last time. This week, we will do the 3rd practice with 3-dimensional solid mechanics problems. All right, that would be another example in 3D. And then from the next week, I will give you a project. So you individually, everyone will work on the project for the rest of the term. All right, any questions, anyone? All right, no questions. So I stop here. Have a good rest of the day, everyone. I will see all of you on Wednesday for our activity. Take care.
Thanks.